The universe keeps secrets that rewrote science itself. 22 forgotten astronomical events, hidden in history, forged the modern world you live in. By the end of this journey, you will see the night sky not as a static picture, but as a living story of overlooked breakthroughs. We will uncover how a Victorian gentleman's solar sketch predicted our vulnerability to global blackouts, and why a persistent radio hiss was actually the echo of creation. What part of our cosmic past are you most curious to reclaim? Before the age of satellites and supercomputers, a single observation by an English amateur astronomer would reveal the sun's hidden fury. On a clear morning in September 1859, Richard Carrington was sketching a group of sunspots when he witnessed something unprecedented. Two patches of intensely bright white light erupted from the solar surface, vanishing just 5 minutes later. A day later, Earth was engulfed. Telegraph systems worldwide failed, with operators receiving severe shocks and papers catching fire from the electrical surges. The night sky, even in the tropics, blazed with auroras so vivid that people could read newspapers by their crimson and green light. This was the Carrington event, a solar superflare of unimaginable power. Yet, for nearly a century, this monumental discovery was relegated to a footnote in astronomical history, a curious anomaly that mainstream science struggled to contextualize. Carrington's meticulous notes were the first concrete evidence of a direct physical connection between the Sun and our planet. He proved that the Sun was not a placid, constant ball of light, but a dynamic and occasionally violent star. This forgotten observation laid the entire foundation for the modern field of space weather. Today, experts like Dr. Emily Levesque point out that Carrington's work fundamentally changed how we see our Sun, transforming it from a mere source of light into a driver of cosmic storms. His records allowed scientists to finally link solar magnetic activity to its tangible effects on Earth, leading directly to the protective systems we now take for granted. Modern power grids, for instance, incorporate specific safeguards designed to withstand the kind of geomagnetic currents that fried the telegraph lines in 1859. These protocols are our direct legacy from that morning in Carrington's observatory. It makes you wonder, with our civilization now so deeply woven into a fragile web of satellites and electronics, how vulnerable are we to the next Carrington-level event? This forgotten glimpse of solar violence was our first warning, a lesson from the past that continues to protect our future. And it all began with one man looking at the Sun and seeing not just light but a storm. Just as Earth was recovering from the Sun's tantrum, another cosmic upheaval was quietly dismantling humanity's entire worldview. In November 1572, a brilliant new star appeared in the constellation Cassiopeia, shining brighter than Venus. For the Danish nobleman Tycho Brahe, this was an impossibility. The heavens beyond the moon were supposed to be perfect and unchanging, a core belief inherited from Aristotle. Yet here was undeniable proof of a violent transformation in the celestial realm. Brahe did something revolutionary. He meticulously measured the star's position and brightness night after night, creating an unprecedented record of its slow fade over 16 months. His data was so precise it proved the object was not a nearby atmospheric phenomenon, but truly a resident of the distant starry sphere. This single observation shattered the ancient doctrine of an immutable cosmos. But the full power of Brahe Supernova was forgotten for generations. While his name became famous, the deeper value of his painstaking measurements was overlooked. Those notebooks filled with numbers became the silent foundation for a scientific revolution. The astronomer Johannes Kepler, who later inherited Brahe's data, used it to derive his laws of planetary motion, proving that planets move in ellipses, not perfect circles. And as historians like Owen Gingerich point out, it was this very chain of evidence, starting with a new star in Cassiopeia, that ultimately allowed Isaac Newton to formulate his universal theory of gravity. Brahe Supernova did more than just break the crystal spheres. Its gradual dimming provided the first recorded light curve of a stellar explosion, a concept that would only be understood centuries later. This forgotten data point became a Rosetta Stone for modern astrophysics, showing astronomers that these cataclysms could be studied and classified. It paved the way for using supernovas as cosmic mile markers, the standard candles that later revealed the expansion of the universe itself. This event forces a profound question: how many of our own deeply held scientific truths might be shattered by a single, unexpected flash in the night sky? The courage to document the impossible, as Brahe did, is what truly propels science forward, and while his star faded from view, its legacy was just beginning to ignite, setting the stage for a discovery that would redefine our very place in the solar system. While Tycho Brahe looked to the stars, another astronomer was gazing at a world that seemed to defy logic. Giovanni Cassini first trained his telescope on Saturn and saw something impossible. The planet's famous rings, which other astronomers had described as solid handles, were not a single, unbroken disk. There was a dark, empty line cutting straight through them. This was the Cassini division, a gap in the rings that should not have existed according to the science of the day. The discovery was so peculiar that for centuries it was treated as little more than a celestial curiosity, a footnote in the grand book of astronomy. Yet hidden within that empty space was a secret law of the cosmos, waiting for the right key to unlock it. That key was gravity. The Cassini division is not really empty. It is a cosmic no-go zone carved out by the relentless gravitational tug of Saturn's moon, Mimas. As Mimas orbits, its gravity pulls on the tiny particles of ice and rock that make up the rings, clearing a path with the precision of a celestial sculptor. This phenomenon is called an orbital resonance. Think of it like pushing a child on a swing. If you push at just the right moment in the swing's arc, you add energy and the child goes higher. But if a ring particle were to try to orbit in the gap, the repeated gravitational nudges from Mimas would be like pushing at the wrong time, kicking the particle out of that orbit entirely. This forgotten observation was the first real evidence that moons could actively shape their environments. It demonstrated that planetary rings were not static decorations, but dynamic, evolving systems governed by the same physical laws that rule the orbits of planets. As planetary scientist Dr. Carolyn Porco explains, Cassini's discovery became the foundational model for understanding ring dynamics. When the Cassini-Huygens spacecraft arrived at Saturn centuries later, it used these very principles to interpret the complex ring structure it observed, revealing countless gaps and waves, all created by the subtle gravitational dances of tiny, hidden moons. This single observation bridges the 17th century to the space age. The same orbital mechanics that clear a path in Saturn's rings guided the Voyager probes on their grand tours of the outer planets, allowing them to use gravitational assists to slingshot from one world to the next. It makes you wonder, as we plan missions to distant star systems, what other forgotten celestial patterns will become the navigation charts for future explorers. This subtle gap in a ring, once overlooked, revealed that the universe is a place of constant gravitational conversation. And it was a conversation that was about to get much louder as scientists began to listen not with their eyes, but with their ears, tuning into the static hiss of the cosmos itself. But the darkness between the stars holds a secret just as profound as any flash of light. For centuries, astronomers accepted the blackness of the night sky as a simple fact, until a German physician named Heinrich Olbers asked a question so obvious it was revolutionary. If the universe is infinite and filled with an endless number of stars, then why is the night sky not a single, solid sheet of blinding light? Every line of sight should eventually end on the surface of a star. This was Olbers' paradox, a puzzle that quietly dismantled the idea of a static, eternal cosmos. The debate it sparked was largely forgotten, overshadowed by later discoveries, yet its resolution would become a cornerstone of our modern cosmic story. The answer lies in the fact that the universe is not infinite in the ways we once assumed. It has both a finite age and is constantly expanding. The light from the most distant stars has simply not had enough time to reach us because the universe is only about 13.8 billion years old. Even more crucial is the expansion of space itself, which stretches the light from receding galaxies, shifting it into the invisible infrared and robbing it of its energy. This phenomenon, known as redshift, was the key that unlocked the mystery. As astrophysicist Neil deGrasse Tyson often explains, grappling with Olbers' paradox directly paved the way for recognizing the significance of the cosmic microwave background, that faint afterglow of the Big Bang. That static hiss is the ultimate answer to the paradox, the cooled remnant of the universe's fiery beginning, stretched and diluted by eons of expansion. This forgotten debate did more than just explain the darkness. It provided a critical philosophical framework for Edwin Hubble's monumental work. When Hubble observed that galaxies were all rushing away from us, their light reddened by the expansion of space, he was providing the observational proof for a concept that Olbers' paradox had demanded. The darkness you see when you look up is not an empty void. It is a historical record. It tells us the universe had a beginning, that it is dynamic, and that it is still evolving. This single, simple question about the night's blackness forced science to confront the grandest truths of existence. It makes you wonder what other everyday mysteries, hiding in plain sight, are waiting to reveal the next great revolution in our understanding. A planet was found with a pen, not a telescope. The year was 1846, and the French mathematician Urbain Le Verrier was staring at a problem. The planet Uranus was misbehaving, straying from its predicted path in a way that could not be explained. While others might have dismissed it as an observational error, Le Verrier trusted the numbers. He performed a breathtaking feat of celestial deduction, calculating that the gravitational pull of an unknown, more distant planet must be tugging Uranus off course. He wrote a letter to the Berlin Observatory, pointing their telescope to a precise spot in the sky. There, within 1 degree of his prediction, they found Neptune. This triumphant discovery was a sensation, but its true, revolutionary impact was soon forgotten, overshadowed by the planet itself. Le Verrier had done something profound. He had proven that the universe could be understood through pure mathematics. He saw the invisible, not by building a better lens, but by following the unerring logic of Newton's laws to their inevitable conclusion. This was the ultimate validation of celestial mechanics, demonstrating that gravity truly was universal, governing the motions of worlds billions of miles away with clockwork precision. Historians of science point out that this single prediction created a powerful new template for discovery. It directly inspired astronomers like Percival Lowell to search for a planet X beyond Neptune, a quest that ultimately led to the detection of Pluto decades later. The method Le Verrier used, called perturbation analysis, became a fundamental tool. It is the same principle that powers our modern hunt for exoplanets. When the Kepler Space Telescope detects a star wobbling slightly, its light dimming by a tiny, rhythmic fraction, it is sensing the gravitational fingerprint of an unseen world, just as Vera sensed Neptune. This forgotten mathematical triumph is the bedrock of our search for hidden cosmic objects, from planets circling distant suns to the mysterious, invisible pull of dark matter itself. How many other cosmic phantoms are out there, their presence betrayed only by the subtle shiver they impart on the things we can see? This predictive power, born from a single planet's wobble, continues to guide our exploration of the dark. And it would soon be needed to decipher an even more violent and brilliant secret, one that would rewrite the entire story of a star's life and death. A star's true story is written in its light, but for millennia we could not read the language. William Huggins changed that in 1868 when he pointed a new instrument, the spectroscope, not at a nearby planet but at the distant star Sirius. He was not just collecting starlight, he was dissecting it, spreading it into a rainbow of colors. And within that rainbow, he saw something that shook the foundations of science: dark lines, a unique barcode etched into the star's spectrum. These lines were the fingerprints of chemical elements. Huggins had identified hydrogen and sodium in Sirius, proving for the first time that the stars were made of the same ordinary matter found here on Earth. This was a monumental blow to ancient beliefs in a special, perfect celestial substance. The heavens were not a separate, divine realm, but a part of our own physical universe. Yet Huggins' groundbreaking role was largely forgotten, overshadowed by the tools he helped create. His work introduced spectroscopy as the fundamental tool of cosmic chemistry, turning astronomy into astrophysics. It gave scientists a way to take the temperature of a star, measure its motion, and even weigh it from millions of light years away. This forgotten technique became the bedrock for the entire classification of stars, leading directly to the Hertzsprung-Russell diagram. That diagram, which plots stars by their temperature and luminosity, is the single most important map we have for understanding stellar evolution. It shows us the entire life cycle of a star, from its birth in a cloud of gas to its death as a white dwarf, neutron star, or black hole. We can now look at the spectrum of a star and know that deep in its core, it is fusing hydrogen into helium, and in its final stages, forging the very elements that make up our bodies and our world. This principle extends far beyond living stars. When a massive star explodes as a supernova, its spectral signature allows us to identify the glowing, expanding remnant it leaves behind. By reading these cosmic barcodes in nebulas and gas clouds, we can trace how the universe has been progressively enriched with heavier elements, the very stuff of planets and life. The astrophysicist Cecilia Payne-Gaposchkin later used this very method to make her own revolutionary discovery, determining that stars are overwhelmingly composed of hydrogen, a conclusion built directly upon the path Huggins first illuminated. What does this tell us? That the iron in your blood and the calcium in your bones were once forged in the heart of a long-dead star. We are not just living in the universe, we are literally made of it. This profound interconnectedness, revealed by a forgotten man and his spectroscope, shows that the cosmos speaks a chemical language we have only just begun to understand. And just as we learned to read the light from the stars, we were about to discover that the universe was also bombarding us with invisible, high-speed messengers from the depths of space. High above the Earth, a lone balloon carried a scientist into a mystery. In 1912, physicist Victor Hess undertook a series of daring balloon flights, armed with instruments to measure radiation. Common sense suggested that radiation, believed to come from the ground itself, would decrease as he ascended away from its source, yet his electroscopes told a different, baffling story. The higher he rose into the cold, thin air, the more the radiation intensified. This was not a terrestrial phenomenon. Hess had discovered that Earth was under constant bombardment from the depths of space, a rain of invisible, high-energy particles he named cosmic rays. His pioneering work was met with skepticism and then largely forgotten, dismissed as a curious anomaly with no practical application. But hidden within that data was the seed of modern particle physics. Hess had proven that the universe is not a quiet void, but a dynamic arena filled with atomic fragments traveling at nearly the speed of light. These cosmic rays, primarily protons and atomic nuclei, smash into our upper atmosphere, creating cascading showers of secondary particles. This forgotten discovery revealed an unseen force that actively shapes our world. It provided the first natural particle accelerator, allowing scientists to study fundamental physics long before massive machines were built. Nobel laureate Dr. James Cronin emphasized how these natural collisions were the precursors to experiments at the Large Hadron Collider, and it was within cosmic ray showers that the first evidence of antimatter, the positron, was found. But the influence of these ghostly particles extends far beyond pure physics. Every time you check the weather, you are seeing their indirect handiwork. The ion trails left by cosmic rays are believed to seed the formation of clouds, influencing global climate patterns in ways we are still unraveling. They are the silent sculptors of our atmosphere. For archaeologists, these rays are a historical clock. The constant production of carbon-14 in our atmosphere, a result of cosmic ray impacts, is the principle behind radiocarbon dating, allowing us to precisely date ancient artifacts and unlock human history. And for our future, this forgotten event is a stark warning. Cosmic rays pose a significant radiation hazard to astronauts, causing potential DNA damage and threatening long-term missions to the Moon and Mars. Shielding against this particle rain is one of the greatest challenges of space travel, so the next time you feel a raindrop, consider that its journey may have begun with a subatomic particle from a distant galaxy striking our sky. How many other invisible conversations between the cosmos and Earth are happening around us right now? This discovery of an invisible ocean washing over us set the stage for an even deeper mystery, one hidden in the very spin of our own galaxy. Two brilliant minds faced off in a debate that would decide the scale of the cosmos. In 1920, astronomers Harlow Shapley and Heber Curtis argued before the National Academy of Sciences over the true nature of the faint spiral nebulae. Were they mere clouds of gas within our own vast Milky Way, as Shapley contended, or were they independent island universes, colossal galaxies of stars far beyond our own, as Curtis insisted? The debate was fierce, its passionate nuances soon forgotten in the wake of a single, definitive answer. Yet this intellectual clash forced astronomy to confront its greatest limitation, the desperate need for a reliable way to measure the unimaginable. The central problem was distance. Without a cosmic yardstick, the argument was purely philosophical. The resolution came from a forgotten tool, the Cepheid variable star. These are stars that rhythmically pulse, growing brighter and dimmer over days or weeks. A brilliant astronomer named Henrietta Swan Leavitt had earlier discovered the key, that the rate of this pulsing was directly tied to the star's true brightness. A Cepheid that pulsed slowly was inherently a brilliant beacon, while one that flickered quickly was a fainter candle. This relationship was a gift to astronomers. By simply timing the pulse of a Cepheid star in a distant nebula, they could calculate its true power. By comparing that to how dim it appeared from Earth, they could finally, accurately measure the vast gulf of space. This method became the foundation of the cosmic distance ladder. When Edwin Hubble later trained the powerful Hooker telescope on the Great Nebula in Andromeda, he was searching for these stellar mile markers. He found them. His observation of a Cepheid variable proved conclusively that Andromeda was not part of our galaxy, but a separate galaxy itself, millions of light years away. In an instant, the universe exploded in size. The Milky Way was dethroned from its central position, becoming just one of countless galaxies adrift in a dark ocean. The debate had forged the very tool that made this revolution possible. The drive to settle the argument accelerated telescope technology and observational methods, directly paving the way for Hubble's law and the stunning realization that all these galaxies are flying away from each other in an expanding universe. This legacy continues today. The Hubble Space Telescope's iconic deep field images, revealing thousands of galaxies in a patch of sky the size of a grain of sand held at arm's length, are a direct descendant of that night in 1920. Each of those tiny smudges contains billions of stars, each a potential sun for other worlds. What does this tell us about the nature of discovery? That truth is often born not from a single eureka moment, but from the friction of opposing ideas, a conflict that forces us to build better tools and see further than we ever thought possible. And as our vision expanded to encompass a universe of galaxies, another forgotten ear was tuning in to the faintest possible signal, a whisper from the very dawn of time. An engineer listening for telephone static found the voice of the galaxy itself. Carl Jansky's task for Bell Labs in 1931 was purely practical, to identify the sources of interference plaguing transatlantic radio communications. He built a strange, rotating antenna he called a merry-go-round, patiently cataloging the expected crackles from nearby thunderstorms, but one persistent hiss refused to go away. It drifted slowly across the sky each day, a sizzle of radio noise that seemed to emanate from the constellation Sagittarius, the direction of our galaxy's heart. Jansky had stumbled upon radio waves from the center of the Milky Way. His discovery was a sensation in the newspapers, but to the professional astronomy community, it was a curious dead end, a phenomenon with no apparent use. They were still focused on light, and the idea of listening to the stars seemed almost absurd. The father of radio astronomy was politely ignored, his breakthrough forgotten for years. But Jansky had thrown open an entirely new window on the cosmos. He proved that the universe was broadcasting on frequencies invisible to our eyes, a symphony of static that held profound secrets. This forgotten noise became the foundation of radio astronomy, a field that would eventually map the spiral arms of our own galaxy by tracing the radio whispers of interstellar hydrogen gas. It revealed bizarre objects like pulsars, the lighthouses of the cosmos, and quasars, the unimaginably bright cores of distant galaxies powered by supermassive black holes. The astronomer Dr. Jocelyn Bell Burnell, whose childhood fascination with Jansky's work led her to co-discover the first pulsar, noted that his legacy was giving us new senses to perceive the universe. This new sense required colossal ears. The Arecibo Observatory, with its vast dish nestled in a natural sinkhole, was a direct descendant of Jansky's antenna, listening for the faintest cosmic signals for decades. Modern radio telescope arrays now stitch together data from dishes scattered across continents, creating virtual telescopes the size of the Earth itself to peer into the hearts of galaxies and study the distribution of dark matter. It was this radio ear that first detected fast radio bursts, incredibly brief and powerful blips of energy whose origins remain one of astronomy's greatest active mysteries. They are the cosmic equivalent of a loud, unexplained knock in the night, compelling us to ask what could possibly generate such a violent, short-lived signal across billions of light years. So the next time you hear static on an old radio, remember that you are listening to the same cosmic background murmur that Jansky first identified. the faint echo of creation mixed with the ongoing conversations of stars and black holes. How many other channels is the universe broadcasting on, waiting for us to build the right receiver to tune in? This shift from seeing to hearing the cosmos prepared us for a discovery that would change our perspective on every planet in the sky, revealing that their very air holds the potential for life. A faint whisper of radiostatic would finally unveil the shape of our cosmic home. In 1951, physicists Harold Ewan and Edward Purcell aimed a makeshift horn antenna built from laboratory supplies at the sky. They were searching for a signal so weak it was considered nearly impossible to detect, a specific radio emission from cold hydrogen gas drifting between the stars. Against all odds, their apparatus registered a gentle, rhythmic hum at a wavelength of 21 centimeters. This was the signature of the most abundant atom in the universe, a beacon from the lonely voids of interstellar space. The discovery was so subtle it was almost dismissed as instrument noise, a forgotten footnote in the march of science. Yet this faint signal became the most powerful cartography tool in the history of astronomy. That 21-centimeter line is a cosmic barcode for neutral hydrogen. It is emitted when the single electron in a hydrogen atom flips its spin, a tiny quantum event that releases a precise amount of energy. Because this radio wave can travel for thousands of light years without being absorbed by cosmic dust, it acts as a perfect tracer for the invisible structure of our galaxy. For the first time, astronomers could see beyond the obscuring dust clouds that block our optical view of the Milky Way's center. By mapping the Doppler shifts in this signal, they could plot the velocity of vast hydrogen clouds, revealing how they orbit the galactic core. The result was a revelation. The Milky Way was not a formless blob of stars, but a magnificent spinning pinwheel with distinct spiral arms. We finally saw our own galactic address. This forgotten hum provided the first concrete evidence of galactic structure and dynamics. It gave us a ruler to measure the distances to other galaxies by detecting their own hydrogen signatures, fundamentally shaping our models of cosmic evolution. The legacy of this discovery echoes in the work of astronomers like Dr. Vera Rubin, who used similar radio methods to measure the rotation of galaxies. Her shocking finding was that the stars at the outer edges of galaxies were moving just as fast as those near the center, defying the laws of gravity unless some invisible mass was holding them together. This was one of the strongest early hints for the existence of dark matter, a mystery born from listening to the hydrogen whispers Ewan and Purcell first heard. Today, this 21-centimeter line is a vital tool for probing the cradles of star birth, the dense molecular clouds where hydrogen collapses to form new suns. It is even the frequency of choice for SETI, the search for extraterrestrial intelligence, on the assumption that any advanced civilization would recognize it as a fundamental signal of the universe. So the next time you look at a majestic image of a spiral galaxy, remember that its map was first drawn not in light, but in the silent radio voice of hydrogen, the primordial stuff from which everything, including us, is made. This profound connection to the raw material of the cosmos would soon be matched by a discovery of our own planet's deep and violent connection to the Sun. The Sun itself seemed to grow sick for more than a year. Beginning in the year 535, civilizations across the globe recorded a terrifying phenomenon. The Sun shone with a feeble bluish light, its heat unable to warm the Earth. Summer frosts destroyed crops from China to Europe, and snow fell in the middle of August. Chronicles from Constantinople to the Andes tell of a mysterious fog that blotted out the sun, leading to widespread famine, plague, and the collapse of empires. For centuries, this was remembered only as a dark age of superstition and suffering, a forgotten historical anomaly. but in the 20th century, scientists found the cause hidden not in old texts but in the ice. Analysis of ancient ice cores from Greenland and Antarctica revealed a staggering spike in sulfate deposits around the year 535. Tree rings from that era showed severely stunted growth across the entire planet. The evidence pointed to a single catastrophic event, a volcanic eruption of unimaginable scale, likely from a volcano like Krakatoa in Indonesia. The eruption injected a massive veil of sulfur dioxide and fine ash high into the stratosphere, where it circled the globe and reflected sunlight back into space for nearly 18 months. This was not just a local disaster, it was a rapid, dramatic planetary cooling event triggered by an astronomical process, the volcanic ejection of material from Earth itself into the sky. This forgotten dimming event became a crucial case study for climate scientists like Dr. Michael Mann, who use it to understand how abruptly the global climate can be shocked into change. It demonstrated with terrifying clarity how a single geological event with cosmic consequences can override all other climate factors, driving temperature shifts that topple civilizations. This historical lesson directly informs modern research into geoengineering, the controversial idea of deliberately injecting aerosols into the stratosphere to combat global warming. The event of 535 is a stark, natural experiment showing both the potential power and the profound risks of such an approach, a global gamble with our atmosphere. The implications stretch even further into space. If a volcanic eruption can do this, what would be the climatic impact of a nearby supernova, bathing our atmosphere in radiation, or the dust from a large asteroid impact? The same principles that caused the global dimming of 535 underpin our modern fears of a nuclear winter, where smoke from burning cities could simulate that volcanic veil and trigger a similar human-made extinction event. It forces us to confront a deeply unsettling question. In our interconnected, densely populated world, how would we survive a sudden, years-long winter imposed from the skies? Our civilization, for all its technology, remains just as vulnerable to a cosmic bad day as the Romans or the Maya were. This event permanently linked astronomy and earth science, proving that our planet's climate is not an isolated system, but a fragile membrane susceptible to forces both from within and beyond our world. And just as we learned how cosmic events could disrupt our measurement of time through seasons, another forgotten discovery was about to show us why time itself is a fluid concept in the vastness of space. A global scientific expedition unfolded not for gold or territory, but for a tiny black dot crossing the Sun. In 1761 and again in 1769, the planet Venus passed directly between Earth and the Sun, appearing as a perfect miniature silhouette against the solar disk. These transits were more than a celestial spectacle. They were a rare opportunity to solve the greatest scientific problem of the age, the absolute size of the solar system. Astronomers realized that by observing the transit from widely separated points on Earth, they could use the principle of parallax, the same way your thumb seems to jump when you view it with first one eye closed, then the other, to triangulate the distance to Venus and from there to the Sun itself. This ambitious project demanded unprecedented global cooperation. Nations that were often at war, like Britain and France, funded coordinated expeditions to the far corners of the world. The most famous of these was Captain James Cook's first voyage on the Endeavour, sent to Tahiti not for conquest but for clear skies and precise measurements. These journeys were brutal tests of human endurance, all for a celestial event that lasted mere hours. The data they collected, when combined, finally gave humanity its first accurate yardstick for the cosmos, the astronomical unit. This was the average distance from Earth to the Sun, a fundamental number that unlocked the true scale of everything from Mercury to Saturn. Yet, for generations, the story of the transit was reduced to a dry calculation, its profound lesson in international collaboration largely forgotten. This forgotten spirit of shared purpose set a powerful precedent. It proved that science could transcend political borders, a radical Enlightenment ideal that directly inspired later projects like the International Space Station, where former Cold War rivals now work together in orbit. The refined orbital calculations from the transits did more than just map our immediate neighborhood. They provided the precise celestial mechanics necessary for the first interplanetary space probes. When Mariner 2 set course for Venus or Voyager 1 headed for the edge of the solar system, their trajectories were calculated using a cosmic map whose first accurate lines were drawn by those 18th-century astronomers staring at a black dot. This cooperative endeavor even laid the philosophical groundwork for the Hubble constant, the measurement of the universe's expansion. To understand how fast the cosmos is growing, you first need to know how to measure distances within it, a problem the Venus transits helped solve on a smaller scale. So what can this forgotten global effort teach us about tackling today's cosmic challenges, like deflecting an asteroid or sending humans to Mars? It shows that our greatest discoveries are never the work of a single nation or a lone genius, but the collective achievement of humanity looking up together. This unified quest to measure our celestial backyard set the stage for a discovery that would reveal the ultimate fate of stars far more massive than our own Sun. A new star blazed in the constellation of Taurus, outshining Venus and visible even at noon. In the summer of 1054, court astronomers in China and Japan meticulously documented this guest star, a brilliant point of light where none had been before. Half a world away, ancestral Puebloan artists in the American Southwest may have carved a depiction of that same event alongside a crescent moon onto a rock face. For nearly 2 years, this cosmic beacon dominated the sky, a silent spectacle witnessed by cultures across the globe. Yet in Europe, despite the clear visibility of the event, it left almost no mark in the surviving chronicles of the time. This collective amnesia in the Western world meant that when a faint, wispy nebula was later discovered in that same spot by telescopes in the 18th century, its explosive origin story had been completely severed. The Crab Nebula was just another cosmic cloud, its incredible history forgotten. The rediscovery of those ancient records centuries later was a revolution. It provided the first undeniable link between a historical supernova and a visible remnant, offering a time-stamped case study of a star's death. Astronomers suddenly had a clock. They could observe the expanding cloud of gas and dust and calculate backwards, confirming that the velocity of the explosion perfectly matched the event of 1054. This forgotten cultural data turned the Crab Nebula into a living laboratory. At its heart lies a pulsar, a city-sized neutron star spinning 30 times per second, blasting out beams of radiation like a cosmic lighthouse. This discovery, as astrophysicist Dr. Robert Kirshner explains, made the Crab a Rosetta Stone for understanding how these stellar corpses can power entire nebulas with their fierce winds of particles. The energy output is so immense that it accelerates subatomic particles to nearly the speed of light, making the nebula one of the brightest sources of gamma rays in the sky, a beacon for space telescopes like Fermi. This single object ties together stellar death, the birth of exotic matter, and the origin of cosmic rays. It even serves as a celestial testbed for Einstein's theory of general relativity, with its intense gravity influencing the light that travels through it. The story of the Crab Nebula forces a humbling question. How much knowledge have we lost because a discovery was recorded in one culture but ignored by another? The Chinese court scribes were not doing science as we define it. yet their precise notations became priceless a millennium later. This fusion of ancient human observation and modern technology reveals a deeper truth that the cosmos does not belong to any one civilization. Our collective view of the universe is infinitely richer when we listen to all the voices who have ever looked up in wonder. This bridge between culture and cosmos reminds us that the sky itself is a shared historical record, one that was about to reveal a different kind of pattern, a rhythmic dance of worlds that seemed to defy gravitational logic. A silent era was accumulating across Europe, stealing days from the seasons with each passing century. By the 1580s, the Julian calendar had drifted 10 full days out of sync with the solar year. Spring arrived later, harvest festivals fell out of step with the equinox, and the entire rhythm of life was slowly coming unhinged from the cosmos. Pope Gregory XIII did not just issue a decree, he performed a surgical strike on time itself. His solution was radical: to simply erase 10 days from existence. In October 1582, people went to bed on the 4th and woke up on the 15th. This was the Gregorian reform, a political and religious upheaval whose profound astronomical heart is now completely forgotten. The controversy was immediate and fierce. People rioted in the streets demanding their 10 days back, convinced the church was stealing a portion of their lives. For the reform to work, it needed more than papal authority. It needed the unassailable logic of celestial mechanics. The core of the problem was the tropical year, the precise time it takes Earth to complete one orbit around the Sun and return to the same position relative to the seasons. The Julian calendar overestimated this by a tiny fraction, just 11 minutes per year. Over 16 centuries, those minutes added up to 10 whole days. The new calendar introduced a more sophisticated leap year system, skipping leap days in century years not divisible by 400. This single adjustment, based on the calculations of astronomers who came before, like Copernicus, brought human timekeeping back into alignment with the cosmic clock. This forgotten event was the first great application of orbital mechanics to daily human life. It proved that to manage our world, we had to first understand its motion in space. This precision became the bedrock of global navigation. When a ship's captain in the 18th century used a sextant to find their longitude, the accuracy of their celestial tables depended entirely on the corrected calendar. That same need for perfect timing echoes today every time your phone pinpoints your location using GPS. The atomic clocks on those satellites must be constantly corrected for relativistic effects caused by their orbital speed and Earth's gravity, a direct descendant of the same principle that corrected the calendar's drift. This reform did more than fix dates. It refined our understanding of Earth's wobble, its precession. That slow, 26,000-year gyration of the planet's axis means that the tropical year is slightly shorter than the sidereal year, the true orbital period. Recognizing this subtle difference was a leap in cosmic self-awareness. Today, climate scientists rely on these precise orbital cycles, known as Milankovitch cycles, to model Earth's ice ages and long-term climate patterns. And when mission control plans a slingshot maneuver for a probe around Jupiter, the trajectory calculations depend on an understanding of time and motion that was forged in the calendar wars of the 16th century. Even the occasional leap second added to our clocks, a correction for Earth's irregular rotation, is a tiny echo of Gregory's 10-day leap. How many of our daily routines, from planting crops to launching rockets, are silently governed by this forgotten celestial agreement? This hard-won alignment between our clocks and the cosmos prepared us to measure something far more elusive, the very fabric of space and time. Light itself was caught moving at a finite speed by watching a celestial clock vanish. In 1676, the Danish astronomer Ole Rømer was meticulously timing the eclipses of Jupiter's moon Io. This moon ducked behind the giant planet with the regularity of a perfect timepiece, but Rømer noticed something strange. As Earth and Jupiter moved farther apart in their orbits, the eclipses would arrive progressively later than predicted. When the two planets swung closer together again, the eclipses happened earlier. The only explanation was that light took time to travel across the vast expanse of space. The delay Rømer measured was not a flaw in the clock, but the time it took for the news of the eclipse to cross the solar system and reach his eyes. His calculation gave the first quantitative estimate for the speed of light, a value that was shockingly fast but undeniably finite. This revelation was initially dismissed by many of his contemporaries, including the influential Giovanni Cassini. How could something be so unimaginably fast yet not instantaneous? The idea seemed to contradict common sense, and Rømer's work faded into obscurity for a time, a forgotten triumph of celestial deduction. Yet this single observation did more than just assign a number to light. It fundamentally altered our philosophical conception of the universe. Proving that light has a finite speed meant that looking out into space is also looking back in time. When you gaze at Jupiter, you see it not as it is now, but as it was roughly half an hour ago. This principle, born from Rømer's eclipse timings, is the bedrock of all modern cosmology, allowing us to peer billions of years into the past by observing distant galaxies. The practical consequences of this forgotten measurement are woven into the fabric of your daily life. Rømer's work directly enabled scientists to precisely define the meter, basing it explicitly on the speed of light. This constant, denoted as c, became the ultimate cosmic speed limit in Einstein's theory of special relativity. As physicists like Dr. Brian Greene explain, the entire elegant relationship between energy, mass, and the fabric of spacetime rests upon this unbreakable limit. Without Rømer's foundational discovery, the development of quantum mechanics would have lacked a critical pillar. The lasers in your DVD player, the fiber optic cables carrying the internet across oceans, and the pinpoint accuracy of the GPS in your phone all rely on our exact knowledge of light speed. Every time your phone triangulates your position, it is performing a calculation that corrects for the time it takes light-speed signals to travel from satellites in orbit, a direct descendant of Rømer's method. This discovery forces a profound question about the nature of reality itself. What does it mean that we live in a universe with a maximum speed limit? It reveals a cosmos where information is not instantaneous, where cause and effect are bound by a universal traffic law. We are forever receiving news of events that have already happened, living in a permanent, slightly delayed version of the present. This finite speed places a fundamental constraint on our communication, our travel, and our very perception of existence. If light traveled infinitely fast, the universe would be a simultaneous, static picture. Instead, Rømer showed us we live in a dynamic, historical narrative where the past is constantly streaming toward us. And just as we learned to measure the light from distant worlds, we were about to discover that the void between them was not so empty after all, filled with a fine dust that held the secrets to our own origins. A star in the southern hemisphere suddenly decided to become a rival to Sirius. In 1843, the massive star Eta Carinae, previously a modest point of light, flared with such violence that for over a decade it was the second brightest star in the night sky. Mariners used it for navigation, and astronomers of the era dutifully recorded its bizarre behavior before it faded once more into obscurity. For nearly a century, this great eruption was catalogued as a mere curiosity, an unexplained tantrum from a distant sun. But its true significance was hidden within the beautiful bipolar cloud of gas and dust it ejected, a structure later named the Homunculus Nebula. This forgotten outburst was not a supernova, but something perhaps even more revealing, a supernova imposter. Eta Carinae had survived its own cataclysm, undergoing a violent transition without fully destroying itself. This phenomenon defined a new class of unstable behemoths known as luminous blue variables. These are stars so massive and so racked by internal pressure that they periodically shed their outer layers in colossal eruptions, losing more mass in a single event than our Sun contains altogether. Astronomers like Dr. Nathan Smith study Eta Carinae as a living fossil, a preview of what stars like it do in the final millennia before they truly explode. Each eruption enriches the surrounding space with heavy elements forged in its core, a crucial process for seeding future generations of stars and planets. The intricate structure of the Homunculus Nebula provides a fossil record of that mass loss, a three-dimensional map of the eruption itself. This single forgotten event fundamentally shaped our understanding of how the most massive stars live and die. It showed that their final years are not quiet, but marked by these violent pre-supernova convulsions. The same physical processes that drive Eta Carinae's instability are now linked to the genesis of the most powerful explosions in the universe since the Big Bang long-duration gamma-ray burst. Understanding this star helps us predict which stellar giants in our galaxy might be next to erupt and what kind of remnant, perhaps a black hole, they will leave behind. This stellar drama directly inspired a new era of time-domain astronomy. Projects like the Legacy Survey of Space and Time conducted by the Vera Rubin Observatory, which will continuously scan the sky to catch stars in the act of transformation. How many other cosmic giants are currently simmering on the verge of their own great eruption? The lesson of Eta Carinae is that the cosmos is not just a place of sudden death, but of turbulent, ongoing rebirth. This focus on a single, volatile star now shifts our gaze to a discovery that redefined the family portrait of our own solar system, proving that our cosmic neighborhood was far more crowded than anyone had ever believed. A new world swam into view, hiding in plain sight for nearly a century. William Herschel's telescope swept across the constellation of Gemini in 1781, settling on a faint, non-twinkling disk. He initially catalogued it as a comet, but its perfectly circular orbit soon betrayed its true identity, a planet beyond Saturn. The discovery of Uranus doubled the size of the known solar system in an instant, shattering the 2,000-year-old doctrine of only 6 planets. Herschel became an overnight celebrity, yet his triumph completely overshadowed a deeper, more humbling truth. Other astronomers had seen it before. John Flamsteed had meticulously charted the same patch of sky almost 100 years earlier, recording Uranus as nothing more than a fixed star, catalogue number 34 Tauri. He saw it, but without the context or perhaps the instrumental clarity to recognize it as a wanderer. This pattern of forgotten predecessors reveals that discovery is rarely a single moment of genius, but a slow, collective dawning of awareness. Herschel's advanced telescope and his systematic sweeping of the heavens provided the final, crucial piece of a puzzle others had already touched. This event forced a profound shift in scientific thinking. If a planet could remain undetected for so long, what else was waiting in the dark? The hunt was on. The precise tracking of Uranus' own slight orbital irregularities, the same method that would later find Neptune, became the standard. This led directly to the prediction and eventual discovery of Pluto, and later to the mapping of the entire Kuiper belt, that vast donut of icy worlds beyond Neptune. Historians point out that while Herschel captured the public's imagination, turning astronomy into a popular pursuit, the real lesson is in Flamsteed's overlooked notebooks. They teach us that scientific priority is often a messy affair, and that every breakthrough stands on the shoulders of forgotten observations. This planetary expansion directly inspired modern voyages to these distant frontiers. The New Horizons mission to Pluto and the Kuiper belt object Arrokoth was a direct descendant of that night in 1781, a robotic extension of our desire to see what Herschel first glimpsed. But it also ignited a debate that burns hotter than ever. What exactly defines a planet? Is it size, orbit, or the ability to clear its neighborhood? The demotion of Pluto from planetary status is a controversy rooted in the questions Herschel's discovery first raised. How many other worlds, just as large and complex, are we still blindly cataloging as mere points of light? The search for Planet 9, a hypothetical giant shaping the orbits of distant Kuiper belt objects, uses the very same celestial detective work that began with Uranus. This expansion of our cosmic backyard was a necessary prelude to hearing the faintest possible signal, a whisper of radiation that would tell the ultimate story of beginnings. Two brilliant radio astronomers were fighting a losing battle against pigeons. Arno Penzias and Robert Wilson at Bell Labs in 1964 were trying to calibrate a supremely sensitive horn antenna, but a persistent, maddening hiss plagued their readings. They scrubbed away what they called a white dielectric material, evicted the birds, and painstakingly eliminated every possible source of interference, from nearby New York City to military tests. Yet the noise remained, a uniform static coming from every direction in the sky, unaffected by the time of day or the season. They had not found a technical flaw. They had stumbled upon the oldest fossil in existence, the cooled remnant of the universe's fiery birth. This cosmic microwave background radiation was the definitive echo of the Big Bang, a discovery born from sheer persistence in the face of frustration. The profound irony is that the very confusion and obscurity of their initial struggle is the part of the story most often forgotten, overshadowed by the grandeur of the final revelation. This faint whisper of radiation, a mere 3 degrees above absolute zero, was the smoking gun. It proved the universe was not eternal and static, but had exploded from an incredibly hot, dense state about 13.8 billion years ago. As the universe expanded and cooled, the initial blaze of energy stretched into the microwave part of the spectrum, creating a ghostly afterglow that now permeates all of space. This finding was the triumphant confirmation of a prediction made years earlier by physicists George Gamow, Ralph Alpher, and Robert Herman, who had theorized that such a background glow must exist if the Big Bang model were correct. Penzias and Wilson had found the missing piece that bridged nuclear physics with observational astronomy. Cosmologist Dr. George Smoot later described how this discovery flung open the door to precision cosmology. By measuring tiny, millionth of a degree variations in this background radiation with satellites like COBE and Planck, we could create a detailed baby picture of the universe, a map of the primordial lumps that would eventually collapse under gravity to form galaxies and clusters of galaxies. This ancient light is now our primary tool for testing the most profound ideas about the cosmos, from the theory of cosmic inflation, a period of faster-than-light expansion in the first fraction of a second, to the nature of dark energy that now accelerates the universe's growth. The static on an untuned television, that familiar snow, is composed of this same primordial light, with about 1% of it directly originating from the Big Bang itself. So the next time you see that screen flicker with noise, remember you are witnessing the faded afterimage of creation. How does it feel to know that your very existence is bathed in the cooled embers of the universe's first moment? This foundational discovery of our cosmic beginning forces us to look forward, to the violent processes that would shape the galaxies we see today, including the dramatic fate of our own Milky Way as it engages in a silent, slow-motion act of galactic cannibalism. Our own galaxy was hiding a fundamental lie about its true composition. In the 1970s, astronomer Vera Rubin and her colleague Kent Ford began a meticulous project, measuring the rotation speeds of stars in the Andromeda galaxy. They expected the stars at the outer edges, far from the galaxy's bright core, to move more slowly, just as Pluto orbits the Sun more sluggishly than Mercury. The pull of gravity weakens with distance, yet their data revealed something impossible. The stars on the galactic fringes were hurtling around just as fast as those near the center. It was as if the entire galaxy was embedded within an immense, invisible sphere of mass, a ghostly halo whose gravity was the only thing keeping these high-speed stars from flying off into the void. This anomaly, the Rubin-Ford effect, was initially met with profound skepticism. The idea that most of the universe's matter was completely invisible seemed more like magic than science. Their careful work was for a time a forgotten curiosity, an inconvenient data set that challenged the comfortable assumption that the cosmos was made primarily of the stuff we can see. Vera Rubin's persistence in the face of this dismissal was a triumph that transcended pure astronomy. As a woman in a field dominated by men, she had already fought countless battles for telescope time and professional respect. Her ultimate vindication became a powerful symbol, inspiring generations of young women to enter science and forever changing the face of modern astrophysics. This forgotten data set is now the bedrock of the dark matter hypothesis. We now understand that the glittering stars and glowing gas of a galaxy are merely the decorative lights on a vast, unseen structure built from matter that does not emit, absorb, or reflect light. The cosmic choreography Rubin and Ford discovered underpins our entire standard model of the universe, the lambda-CDM model, which states that dark matter and dark energy together make up 95% of everything. Particle physicists like Dr. Lisa Randall now design elaborate experiments to hunt for the proposed weakly interacting massive particles, or WIMP, that could be the building blocks of this dark cosmos. Supercomputers run simulations of the universe's evolution that simply do not work unless they include this invisible scaffolding, whose gravitational pull guided the formation of the very galaxies we see today. So what does it mean that we are surrounded by an ocean of matter we cannot touch or see? It means our cosmic identity is profoundly humble. We are not made of the universe's primary substance, but are merely a rare, visible afterthought. Every galaxy is a lighthouse in a dark sea, and we are just beginning to learn how to navigate by the unseen currents that truly govern the cosmos. This profound mystery of the invisible majority now draws our attention back to our own solar system, to the ancient dust and ice that hold clues to a different kind of formation. The edge of our solar system was no longer an empty void, but a bustling celestial highway of ancient ice. In 1992, astronomers David Jewett and Jane Liu confirmed a faint, slow-moving dot beyond Neptune, the first direct evidence of the Kuiper belt. This discovery validated a 50-year-old hypothesis, one whose original architects, Kenneth Edgeworth and Gerard Kuiper, had been largely forgotten. Their theoretical work proposed a disk of leftover planetary building blocks orbiting in the deep freeze, a prediction that was ignored for generations. Finding this belt of icy worlds did more than just add new objects to a chart. It fundamentally rewrote the story of our solar system's violent youth. This vast reservoir is the source of short-period comets, those icy visitors like Halley whose journeys are now traced back to this distant neighborhood. The sheer number of these objects revealed that the solar system extends dramatically farther than the 8 planets, a realization that forced a dramatic realignment of Pluto's status from a lone planet to the king of this icy realm. As planetary scientist Dr. Alan Stern explains, this discovery was the direct scientific impetus for the New Horizons mission, which gave us our first breathtaking close-ups of Pluto and the primordial peanut-shaped world Arakoth. These are not mere frozen rocks, they are perfectly preserved fossils from the dawn of the solar system. The structure of the Kuiper belt provided critical clues for the NICE model, a revolutionary theory of planetary migration. This model suggests the giant planets did not form in their current positions, but shifted dramatically, their gravitational dance scattering countless icy bodies inward in an event known as the Late Heavy Bombardment, which pelted the young Earth and Moon with asteroids. The strange, clustered orbits of some Kuiper belt objects are the lasting fingerprints of that ancient upheaval. They are the celestial evidence that our solar system was once a far more chaotic and dynamic place. How many other planetary systems orbiting distant stars contain similar belts of icy debris, each holding the untold history of its own formation? These distant, frozen relics tell us that our cosmic neighborhood is not a static arrangement, but the enduring result of a gravitational storm that settled billions of years ago. This belt of frozen secrets sets the stage for a discovery about a far more local and far more consequential impact, one that literally shaped the course of life on our planet. A remote forest in Siberia simply vanished in an instant. On June 30th, 1908, a fireball brighter than the sun tore across the morning sky, culminating in a blast that flattened 800 square miles of trees, knocking people off their feet hundreds of miles away. The seismic shockwave registered across Europe and Asia. Yet, for nearly 2 decades, the Tunguska event remained a scientific ghost story, an unexplained cataclysm in a region so isolated that no formal expedition could reach it. When researchers finally arrived, they found a scene of unimaginable devastation, with trees scorched and laid out in a radial pattern, all pointing away from a central epicenter. The most baffling clue was what was missing. There was no crater. This forgotten explosion was not an impact but an airburst. A relatively small object, likely a stony asteroid or a comet fragment no more than 200 feet across, had entered Earth's atmosphere at over 30,000 miles per hour. It superheated the air around it, detonating 3 to 6 miles above the ground with the force of a 10 to 15 megaton bomb. The energy released was 1,000 times more powerful than the atomic bomb dropped on Hiroshima, all from a cosmic pebble. The astronomical significance of this was lost for decades, dismissed as a one-in-a-million fluke. But Tunguska was a live-fire demonstration of a threat we had never truly considered, the danger from objects too small to easily spot, but large enough to devastate an entire region. This single event fundamentally reshaped our understanding of planetary defense. It proved that an asteroid does not need to hit the ground to cause catastrophic damage, that the atmosphere itself can become a weapon. As astronomer Dr. Phil Plait emphasizes, Tunguska is the definitive case study for why we need robust asteroid detection systems. It directly inspired the creation of NAS, a Near-Earth Object Observations Program, which tirelessly catalogs and tracks potentially hazardous asteroids. The memory of that Siberian forest drives the development of advanced survey telescopes like Pan-STARRS in Hawaii, which scans the heavens nightly, automatically flagging new moving objects. The data it collects is our first line of defense, an early warning network for the cosmos. The legacy of Tunguska is not just in watching the skies, but in learning how to act. It provided the foundational risk assessment for impact hazards, quantifying the statistical probability of such events and their potential effects on climate and ecosystems. A similar airburst over a populated city today would result in millions of casualties. This sobering reality fuels the development of active defense technologies, like the Double Asteroid Redirection Test or DART mission, which successfully proved that a kinetic impactor could nudge an asteroid off course. The same principles that shattered the Tunguska sky are now being used to design our planetary shield. The more recent Chelyabinsk event in 2013 was a stark reminder, a smaller but equally unexpected airburst that injured over 1,000 people with its shockwave. It was a cosmic echo, a smaller version of Tunguska that proved these are not rare historical anomalies but ongoing events. So how prepared are we really for the next cosmic impact? We have the blueprints for protection, but the political and global will to fully fund and implement a comprehensive planetary defense system remains a work in progress. This forgotten explosion in a distant forest serves as a permanent warning that our world exists within a cosmic shooting gallery. It is a lesson in humility and a call to action, one that leads us to the final, most profound forgotten event, a discovery that redefined our ultimate origins and our place in the cosmic story. A simple printed pamphlet shattered the cosmos into 1,000 pieces. In 1610, Galileo Galilei published his Sidereus Nuncius, or Starry Messenger, and the heavens were never the same. He announced that Jupiter had its own 4 attendant moons, a miniature solar system in itself, and that our own moon was not a perfect, smooth sphere, but a world of jagged mountains and deep craters. While his confrontation with the Church is legendary, the deeper, more subtle revolution he sparked in the very practice of science has been largely forgotten. This was not just a book of discoveries, it was a user manual for a new way of seeing. Galileo did not merely report what he saw, he published detailed engravings of his observations, inviting anyone with a telescope to verify his claims. He turned the sky into a public laboratory. This act of radical transparency created a new culture of evidence-based debate, directly challenging the ancient authority of scholarly texts. Historian Dava Sobel emphasizes that Galileo essentially founded the concept of citizen science, empowering anyone with the right tool to participate in the grand project of understanding the universe. The demand for telescopes exploded. Lenses that were once curiosities became essential instruments of discovery, forcing a rapid global improvement in optical technology. The same grinding techniques used to perfect astronomical lenses were soon applied to create the first powerful microscopes, revealing a hidden universe of life teeming in a drop of water. This forgotten technological cascade, from stargazing to germ theory, began in the public fervor that followed the Starry Messenger. The acceptance of a sun-centered solar system became inevitable not simply because of Galileo's arguments, but because his method allowed others to see the evidence for themselves. This reliance on observable, repeatable data became the bedrock of the scientific method, a legacy that directly enabled Isaac Newton to formulate his laws of motion and universal gravitation just a few decades later. The precedent Galileo set for open data sharing now lives on in modern projects like Zooniverse, where millions of online volunteers classify galaxies and transcribe ancient weather logs, proving that the collective power of curious minds is our greatest scientific instrument. So as our journey through these 22 forgotten events concludes, we are left with a final, powerful question. How many future breakthroughs are waiting, not for a lone genius, but for the right tool to be placed in the hands of everyone? Galileo's true triumph was to show that the universe is not a secret to be guarded, but a mystery to be shared, a legacy that continues to guide our search for truth among the stars. Behind every great discovery in astronomy lies a chorus of quiet voices, the amateur observers whose notebooks filled the gaps between the moments of professional triumph. While names like Galileo and Hubble echo through history, countless volunteers have spent their nights tracking the slow pulse of variable stars or the sudden appearance of a new comet, their patient work forming the bedrock of long-term cosmic studies. These enthusiasts provided something the grand observatories could not: continuous coverage of the sky. A professional telescope might be scheduled for a specific, high-priority target for only a few nights a year, but an amateur with a backyard scope could monitor the same star for decades, building a priceless record of its subtle changes. This dedication created vast archives that professional astronomers now rely upon. The American Association of Variable Star Observers, for instance, has amassed millions of measurements over more than a century, a data set that has been crucial for understanding stellar life cycles and even for detecting the subtle dimming caused by exoplanets transiting distant suns. Their records of comet trajectories have refined our models of the solar system's small bodies, while their observations of nova and supernova light curves provide the first alerts that trigger global professional follow-up. This is the forgotten legacy of community science, a global network of dedicated eyes that has fundamentally shaped our understanding of cosmic time. How many of our modern insights into climate, drawn from historical sunspot records, or our alerts about potentially hazardous asteroids, depend on the meticulous logs kept by these unsung heroes? Their work proves that the universe reveals its secrets not just in brilliant flashes, but in the patient, accumulated glow of 1,000 small observations. This collective endeavor, spanning centuries and continents, is the true fabric of astronomical progress, a reminder that every curious person who looks up contributes to the greatest story ever told. These 22 forgotten events are a testament to a simple, profound truth, that our map of the cosmos was drawn in invisible ink. From Carrington's solar storm to the static hiss of the Big Bang, each breakthrough was initially a whisper, an anomaly dismissed by the mainstream. They reveal that scientific progress is not a straight line of eureka moments, but a winding path paved with persistence, luck, and the courage to question the obvious. These stories urge us to look beyond the famous names and celebrate the quiet observers, the meticulous note-takers, and the stubborn questioners who saw what others ignored. They teach us to value the long arc of history, understanding that today's baffling data point might be tomorrow's revolution. So the next time you gaze at the night sky, remember that its darkness is not empty. It is filled with the echoes of these forgotten milestones, each one a stepping stone that brought us closer to understanding our place in this vast, unfolding story. Which of these hidden histories resonated most deeply with you? Share your thoughts in the comments below, and if this journey through cosmic memory has sparked your curiosity, subscribe for more explorations into the secrets of space. By remembering these legacies, we do more than honor the past. We become active participants in the next great chapter of discovery, ensuring that no future flash of insight is ever lost to time.